let's introduce some terminology to explain how concatenating data frames in series works. Let's consider stacking two-dimensional arrays first. We'll create three matrices by creating a range of consecutive integers using range, transforming a one-dimensional array into a rectangular shape with the reshape method, and adding different constants to make them easy to distinguish. That is, we make a 2x4 matrix A, a 2x3 matrix B, and a 3x4 matrix C. We can stack the 2x4 matrix A and the 2x3 matrix B horizontally using np.hstack. The input is a list of NumPy arrays. Equivalently, we can use np.concatenate with the same sequence and axis equals 1 to append columns horizontally. In both cases, both A and B must have the same number of rows, although the number of columns can differ. We can also stack the 2x4 matrix A and the 3x4 matrix C vertically using np.vstack or np.concatenate with axis equals 0. Again, it's important here that both matrices have 4 columns. The argument axis equals 0 is actually the default and optional. A value error exception is raised when the arrays have different sizes along the concatenation axis. For instance, trying to stack arrays A and B horizontally or A and C vertically causes problems. Let's return to the population and unemployment data indexed by zip code. When loaded, population has 4 rows and 1 column, while unemployment has 4 rows and 2 columns. Again, the indices of these two data frames differ in all but one row with zip code 2860. Remember, Pandas was developed after NumPy. Let's pretend we've received these data frames as NumPy arrays by converting them to arrays with the NumPy np.array constructor. When we do this, the index information is lost. There are simply two NumPy arrays of dimension 4x1 and 4x2. We could apply np.concatenate or np.hstack to these two arrays to yield a new array of dimension 4x3. But this result is meaningless. The rows are glued together independent of the original meanings. We would have to store the zip codes in other lists or arrays to align rows properly. It turns out that appending labeled tables in this way corresponds to what is called a database join. Joining tables involves meaningfully gluing indexed rows together. We'll look at more types of joins later, but let's focus on outer and inner joins now. An outer join preserves the indices in the original tables, filling null values for missing rows. An outer joined table has all the indices of the original tables without repetition, like a set union. Conversely, an inner join has only index labels common to both tables, like a set intersection. Let's make this concrete with the population and unemployment data frames. We call concat along axis equals 1 and explicitly specify join equals inner for an inner join. This means only the row label present in both data frame indexes, 2860 in this case, is preserved in the joined data frame. The column values in this single row are filled in from the corresponding columns from the population and unemployment data frames, respectively. When we specify join equals outer when concatenating along axis equals 1, we get an outer join. This is the behavior of concat we originally observed because, if unspecified, the join parameter defaults to outer. All row indices from the original two indexes exist in the joined data frame index. When a row occurs in one data frame but not in the other, the missing column entries are filled with null values. Notice we could also do an inner join along axis equals 0 instead. The resulting data frame is empty because no column index label occurs in both population and unemployment. Try your hand now at computing inner and outer joins when concatenating data frames in the exercises.